Hi, welcome to my talk about Objective Observer Relative Flow Visualization in curved spaces for unsteady 2D geophysical flows. I know that's quite a long title, but let me try to show you an example. For instance, when we look at a hurricane on the Earth's surface, a location-centric visualization would keep the Earth static and the hurricane moving, while a feature-centric visualization would keep the hurricane at the center of the visualization static and move the Earth underneath. One benefit of our approach is that we can switch from a location-centric visualization to a feature-centric visualization. Here we show a result of our approach that illustrates the difference. First, we see how a hurricane moves while the observer is kept static relative to the Earth. When we visualize the hurricane from the perspective of an observer that moves with it, the Earth moves underneath and the flow stays in place. This can be useful for visualization, but also for computation of certain characteristics of the hurricane. The change of the observer does of course not change the phenomenon itself, but only how it is perceived. Here we compare the actual trajectory of the hurricane, shown on the left, with the motion of the observer that was computed by our approach on the right. We can see that the computed observer closely follows the center of the hurricane over time. The question is, how do we find such an observer that moves with the hurricane, and what is an observer anyways? For instance, a satellite that rotates around the Earth perceives different relative velocities than an observer that is moving with the Earth. When we keep the satellite static, the Earth appears to rotate in the opposite direction. This rotation corresponds to a time-independent rigid motion. When we observe the Earth from the perspective of an aircraft, we see the Earth rotation changing over time, which corresponds to a time-dependent rigid motion observer. Rigid body motions on smooth manifolds can be described with Killing vector fields, named after Wilhelm Killing. We use these Killing vector fields to model rigid body observers on the sphere and on other curved manifolds. Now that we know how to represent such an observer mathematically, the question is, how do we compute an observer that moves with a feature such as a hurricane? For a feature-centric visualization, we are trying to find an observer that follows a feature in the flow field. Here we see an illustration of a dataset where a vortex moves across the spatial domain. Our goal is to find an observer that perceives the vortex to stay in place. This observed flow field is a steady flow field that does not change over time. Conventionally, a partial derivative is used to compute the time derivative of a flow field, but here we need to find the time derivative of the observed flow field. We derive a new differential operator called the observed time derivative, which equals the partial time derivative plus the Lie derivative. Let's ignore the mathematical details for now. The important thing here is to keep in mind that we do not know the observer that minimizes the time derivative, so we cannot simply use the partial derivative. Instead, we have to define the observed time derivative and use this differential operator in an optimization procedure to find the observer that perceives the flow field to be as steady as possible. So let me briefly review what we have learned so far. We know for a fact that all velocities are relative to an observer. We assume that physical phenomena like hurricanes are captured in the flow data, and that changing the observer does not change the phenomenon. So no matter how a phenomenon was observed, if we compute a feature-centric visualization, the result should always be the same. This property that we require from our approach is called objectivity. Let me explain this property visually. Let's say we have a vortex on the sphere. Here we visualize this 2D vortex with path lines that move outward over time. So we use the third dimension to visualize time here. All the straight lines going outwards mean that nothing is moving in these regions, and only at the center we see the vortex. Let's look at the vortex from a different perspective. We take this vortex, now only shown with 3 path lines, and see how it would look observed from an aircraft that passes by. If the aircraft flies 1/8 around the sphere, this is what the aircraft would perceive. For 1/4 of a rotation, this is what the aircraft would perceive. And for a full rotation, this is what the aircraft would see. The results are 4 very differently looking flow fields, but we know they all contain the same phenomenon. What we require from our feature-centric optimization is that it compensates for these different observers. So no matter which of these input fields we take, when we minimize the observed time derivative, we require that the optimal observer field is compensating for the different inputs. When we use the different observer fields in our observer-aware visualization, the outcome is always the same. In the paper we showed that the observed time derivative fulfills this property and that our feature-centric visualization is objective in this sense. So far we have only considered rigid body observers. When we look at real-world phenomena, we see that they are typically not perfectly rigid. Since we do still want to follow these phenomena, we can relax the observer specification a little bit and use a as rigid as possible observer. The good news is that while killing fields only represent perfectly rigid motions, approximate killing fields can be used to represent deforming motions. Similarly to killing fields, we can use them to represent observers. We can co-minimize the deformation as a second term in our optimization. An optimization parameter gives us control of how much deformation is desirable. In the paper we show that the property of objectivity carries over to approximate killing fields as well. Here we visualize how an approximate killing field deforms the spatial domain. We show a visualization of the approximate observer field in the upper right. We can pick a single observer from the approximate killing field and use it as a rigid motion observer. The rigid motion observer is visualized in the center. When we observe the input dataset from the perspective of the rigid motion observer, we obtain a feature-centric visualization without deformations. Our mathematical framework as well as the implementation of the approach are fully intrinsic. This means we can compute everything in 2D. It works for flat as well as for curved manifolds. We can perform all computations which are related to the curvature of the manifold purely analytically. Since the flow field data is typically given discretized, we need to approximate the derivatives numerically using a triangulation of the manifold. Manifolds are in general represented with 2D charts, which provide a linearization of the curved space. Here we see the 6 charts that we use to represent the sphere. The charts are triangulated and are used for the optimization of the observer field as well as the visualizations of the observed flow fields. Here we show another example on the sphere. A vortex street is moving from left to right. Note that line integral convolution cannot be used to visualize the vortices. In blue and red we color-coded vorticity to show the moving vortices. From this field we compute an approximate observer field and show how it perceives the input field. Note that the input field is transformed to become nearly steady and that line integral convolution now clearly shows the vortices. Our approach also works on other curved manifolds. Here we show a cylinder with a moving vortex. It is interesting that line integral convolution can only visualize instantaneous velocities and therefore shows the center of a moving vortex at the wrong position. It is also hard to see the swirling motion using path lines. Here we visualize the observer field that follows the vortex around the cylinder. When we visualize the input field relative to this observer field, we see a vortex that stays in place. The center of the vortex is now shown at its actual location. Let me close with an open question about our research. Here I show the high-level overview of our visualization approach that I have presented today. We take an input flow field, feed it to our optimization procedure to compute an observer field that minimizes the observed time derivative to ultimately get an as steady as possible observed flow field. What we implicitly assumed here with our approach was a very specific intention of the user. We assumed that we want to generate a feature-centric visualization. So the question is, which other user intentions would lead to a meaningful specification of the observer and, as a consequence, result in novel use cases of observer relative visualization? This is one of the open research directions that we would like to investigate in the future. In this talk, I have tried to get some general concepts across that are related to observer relative flow visualization. While I gave a rather high-level explanation of our approach, I would like to encourage you to also have a look at our paper, where we cover many more details. Our framework uses concepts from differential geometry and mathematical physics. We use this mathematical language to define the important property of objectivity, as well as a novel differential operator, the observed time derivative. Further, the paper points out subtle differences, such as the use of the covariant derivative to compute the velocity gradient tensor on curved spaces, which is the generalization of the commonly used Jacobian. We believe that our general mathematical framework will provide a solid foundation in the future. It can be used for novel observer-aware flow visualizations and computation methods on smooth manifolds, no matter if they are flat or curved. Thank you for your attention, and please visit us at vccvisualization.org.